All right, let's dive right in. If you've ever found yourself looking at a database or a spreadsheet, and you've wondered how a simple idea in your head actually becomes a result on the screen, well, you are in exactly the right place. Today, we're going to build the essential toolkit for telling computers precisely what to do with our data.
So here's the thing. We all know computers work with data. We see it in tables all the time. But how do we actually talk to the computer? How do we translate a simple thought into a command that a machine can execute perfectly, every single time, with absolutely zero confusion?
And the answer, really, boils down to one single critical idea: precision. See, unlike a person, a computer can't guess what we mean. It can't infer or read between the lines. It is perfectly, completely literal. And that means our instructions have to be just as perfect. And this comparison just hits the nail on the head. We can tell a friend, hey, go find this book, and they just get it. They know what that means. But a computer? No way. It needs the instruction on the right. A clear, mechanical, step-by-step process. It needs to know exactly where to start, exactly where to stop, and exactly what to do at every single point in between.
Okay, so this absolute need for precision leads us straight to our very first tool. We've got to have a way to wrap up these super detailed instructions into a neat little package so we don't have to write them out from scratch every single time.
I mean, seriously, can you imagine writing out that whole for each index I thing every time you needed to find something? No, thank you. So how do we solve this? How do we package these instructions so we can just call on them whenever we need them? We do it with something called a procedure. Now, you might have heard other names for it, like a function or a method. They all kind of mean the same thing. Honestly, the best way to think of it is like a recipe. You give it a name, right? Like find my book. It takes in ingredients, we call those parameters or inputs, and then it gives you back a finished dish, which we call a return value or an output. And this breaks it down perfectly. Every procedure has these three key parts. You've got the inputs, that's the data it needs to get started. You've got the process, that's our ultra-precise recipe, the step-by-step instructions. And you've got the outputs, the result it hands back when it's all done. It's simple, it's powerful, and best of all, it's reusable.
So we've handled the instructions. We've got our recipes all packaged up. But a recipe is pretty useless without ingredients, right? So the next big question is, how does a computer actually see and organize the data we wanted to work on? This is such a great question, especially for those of us who are used to working with databases. We look at our data and we see these beautiful, neat rows and columns. But is that what the computer sees? So here's a data table that should look super familiar to pretty much all of us. Each row has an index number and each row has some data. We can just glance at it and see, yep, index 4, that's James Madison. It's totally straightforward for us humans. Okay, now this is where things get really interesting. This slide shows how an algorithm views that exact same data. It doesn't see a table, it sees something called an array. An array is basically just a numbered list of items. So to get the data for James Madison, an algorithm doesn't ask for row 4, it asks for the element at index 4 of array A, or as you see it written there, A bracket 4. And this right here, this is the superpower of arrays. This is so important. It doesn't matter if we want the very first element in the array or the 5 millionth element. The computer can jump directly to any index in the exact same amount of time. This is incredibly efficient, and it's a huge reason why algorithms can process massive amounts of data so quickly.
All right, quick recap. We can package our instructions into procedures, and we can organize our data into arrays. Now it's time to put those two things together so we can work through an entire set of data. I mean, accessing a single element is great, but that's rarely what we need to do. How do we check every single element in our array? How do we tell our procedure to go through all of them, one by one, from the very beginning to the very end?
Well, the most common way to do this is with a loop. And a loop is pretty much exactly what it sounds like. It's just a structured way of telling the computer, hey, do this action. Now do it again and again. And each one of those repetitions has a name. It's called an iteration.
And the for loop is the classic workhorse here. It's the one you'll see all the time. It's really simple. You give it a variable to count with, you tell it where to start and when to stop, and it just executes your instructions for every single value in between. It's a systematic way to guarantee you visit every item in your array. So that step-by-step, one after the other approach feels pretty intuitive, right? But is it the only way? Is there maybe a different way to think about working through a whole bunch of data?
You bet there is.
And it's a concept that's, well, it's a little bit of a brain bender at first, but it is unbelievably powerful. It's called recursion. And with recursion, a procedure solves a problem by basically calling a copy of itself to solve a smaller piece of the exact same problem. So let's think about it with these analogies. A loop is like walking down a bookshelf, checking each book one at a time. It's linear, it's sequential. Recursion is more like a set of those Russian nesting dolls. You open the biggest doll, and what's inside? A smaller, identical doll. And you open that one, and so on, until you get to the tiny little one in the middle.
Now, for recursion to actually work and not just go on forever, it needs two absolute must-have rules. First, it needs a base case. That's the condition that tells it when to stop. It's the tiniest doll, the one that doesn't open. Second, each time it calls itself, the recursive call, it has to be on a slightly smaller version of the problem, so you know you're always getting closer to that base case.
Okay, let's pull all this back and put it all together. What we've really been doing here is assembling a foundational toolkit for describing exactly how algorithms work.
And there you have it, 4 fundamental tools. You've got procedures to package up your instructions, you've got arrays to organize your data, and then you have 2 fantastic ways to process that data: loops for going step by step, and recursion for solving by self-reference. With just these 4 concepts, you have the foundation to build almost any algorithm imaginable.
And that is the real takeaway here. These concepts are the basic grammar you use to write the stories that your data can tell. So the question isn't just about what we've learned today, but what incredible, complex problems, from searching to sorting and way beyond, can you now start to solve with this toolkit? Hey, if this helped build out your own mental toolkit, do me a favor and hit that like button. Share it with someone else who's also trying to understand the language of data, and of course, subscribe for more explainers that break down these kinds of complex topics. Thanks so much for watching.